Let's take a look now at solving systems of linear equations using the graphing method. Whenever you have a linear equation, the graph of that equation is a straight line. So for example, let's say we were going to graph 2x minus 3y equals to 6. Well, we could graph that by either finding individual solutions and plotting our points, or we can write this in slope-intercept form and do it that way. Either way, we're going to get the equation of this. We're going to get the graph of this equation. So here, let me go ahead and do this by using the slope-intercept form. If I subtract 2x from both sides, these subtract off, giving us minus 3y equals to 6 minus 2x. Here we typically write the variable first, so let's say minus 2x plus 6. And then we can go ahead and divide everything by a negative 3 to isolate our y. So those divide out. Now we're left with y equals negative divided by a negative, that's a positive 2/3. You have an x right there. And then 6 divided by negative 3 is negative 2. Okay. And that gives us everything we need to graph our line. So let's go ahead and graph this. All right, let's see here. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, like that. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, and 1, 2, 3, 4, 5, 6, 7. All right. So because you have a constant of negative 2, that means our y-intercept will be the point 0, negative 2, down here. Or in other words, if you plug in x is equal to 0, that's 0 minus 2. Oh, okay, so if x is 0, y must be negative 2. So 0, negative 2 is your y-intercept. Then your slope of 2/3 tell you that from this point, to get to another point, you can go up 2 steps and right by 3. The top number tells you up or down, where positive is up and negative is down. The bottom number tells you left or right, which positive is to the right, negative is to the left. So this tells you 2 up and 3 right. So 1, 2, and then over 1, 2, 3. And we can connect our dots, and that gives us our result. Oh, let's see here. Let's see if I can line that up well. Maybe, maybe not. That should be okay right there. All right. So now, what if we had a different line? Well, then it would have a completely different equation. For example, if I had x plus 3y equals to 12, well, that would have a completely different equation, yeah? So, go ahead and give that a try. Pause the video and graph this linear equation. Go ahead and graph it on the same graph that you have here. As you're taking your notes, you've created this graph. Be careful and take the extra time to draw this as carefully as you can, because we're going to be using the graphs of these for something in just a moment. So go ahead and do this on the same plot. Pause the video, and once you have your result, go ahead and unpause and we'll go through it together. All right, so same idea. We're going to go ahead and isolate our y to put this in slope-intercept form. We can subtract our x from both sides of the equation. They'll subtract off, giving you 3y equals, you have your negative x, which is the same as saying negative 1x, and that's a positive 12, so we can say plus 12. And then we're going to go through and divide everything by a positive 3. Now remember, negative x is like saying negative 1 over x, like that. Negative 1 times x, rather. So here, these 3's divide away, and that gives you just your y. Here, negative 1 over 3, well, that's negative 1/3, don't forget your x. And then a positive 12 divided by 3 is a positive 4, just like that. So now that can be graphed. Again, we have an intercept of 0, comma, that number right there, in this case 0, 4. And then we can use this to find another point on our graph. That's a negative 1 over 3. So remember, the top number tells you up or down. Since that's a negative, you're going to go down by 1. And the bottom number tells you left or right. That's a positive 3. That's a negative 1 over a positive 3. So you're going to go to the right by 3. So from here I can go down 1 and then write 1, 2, 3. Right about there. And now I can graph that result on my page here. And that's a straight line as well. All right. Now notice that these two lines don't really have anything in common other than being lines. They're both linear graphs of linear equations. Notice that their solutions are very different and completely separate from one another. However, you will notice that there is exactly one point which they do share as a solution. This point right here. This point is the one and only point that is a solution to both of these equations. We know that because it's a point that's on. Because this point exists on both of these lines, it is a solution to both equations, and we call this the solution to the system of equations. Whenever you have two or more equations together, it's called a system of equations. Any solution that works for all of the equations in that system is the solution to the system. Solution to a system of equations. Notice right here we had two systems of equations, and I can find one point where they cross, meaning there's one point where the two equations are solved. This can be found very readily if we can just read the graph. Notice to get to that point, we're going to go over 1, 2, 3, 4, 5, 6 steps to the right, and then we're going to go straight up. Well, let's see, that's 1, 2 steps. So 6 to the right, up by 2. That's going to be the point 6, 2. So that is our solution to our system. Notice that if we substitute these into our equations, they should work for both. In fact, they have to work for both. If they don't, then this is not really the solution to the system. Let's go ahead and give that a try. Let me go ahead and check to make sure that I've done this correctly. Again, if that is the right solution, it should just make this equal to 6. So let's find out. That's going to be 2 times 6 minus 3 times 2. I'm just plugging in x and y. Let's see what happens. 2 times 6 is 12, minus 3 times 2 is 6, and 12 minus 6 is 6. Yeah, that's exactly what we thought we should get. This is equal to 6. So that works. Go ahead and check the remaining one. Make sure that this is a solution to the other equation. Go ahead and give that a try. Pause the video, and once you're done, go ahead and unpause and we'll confirm it together. All right, we can go ahead and check this one as well. Note that if you substitute in x is equal to 6 plus 3 times that y is equal to 2, that should equal to 12. Well, let's see. That's already just the number 6. We don't need to do anything to it. Here, 2 times 3 is 6. And sure enough, if you add 6 plus 6, you get 12. So even though these equations are completely different equations with a completely different set of solutions, there is that one solution that is common to both. It is the solution to the system of equations. Now, systems of equations can fit into many different categories and can have many different results. However, if we are only dealing with linear equations, meaning the equations are straight lines, then that simplifies things greatly. There are only 3 possible outcomes when you have a system of linear equations. Those 3 outcomes are when we have a system of 2 linear equations in 2 variables, which is all we're going to be dealing with right now. The only possibilities are what we just saw, namely that your system has a single solution. because the two graphs crossed at exactly one point. And that one solution might be different depending on your system, but there's only one. The next possibility is that there are no solutions. It is possible that if you have two linear equations, that the place where they cross, the point that they have in common, just doesn't exist. And that occurs if you have two parallel lines. If your two lines are parallel, they never get any closer together, they never get any further apart, which means they will never cross. So in the case of no solutions, it's because you have two parallel lines. Finally, the third outcome is, again, you have two linear equations in your system. It's possible that even though the two equations are different from each other, that they have all the same solutions. So it's possible that one of your equations might graph as this line here, and the other equation might graph as this line here. And even though the equations are different, it turns out that all of their solutions are the same. They have a common set of solutions. In this case, you have two coinciding lines, two overlapping lines, and you have infinitely many solutions. Here, any point that is on these lines is a solution. This point here, and this point here, and this point here, every point that happens to be on those lines, which is going to go on forever in both directions, all of those points are solutions. So you do have infinitely many solutions to your system. Now, we are going to have to be a little more specific when we get to a problem like this. Whenever we have a problem which has just one solution, well, then we can simply state that solution. For example, up here we said 6, 2, or 2, 5, or 9, -6, or whatever the solution might be. When we have no solutions, well, then we simply state there are no solutions, and then we're done. However, when you have infinitely many solutions, you can't just state the solutions because there are infinitely many. You'll never finish. But you also can't just say there are infinitely many solutions. You say, well, why not? It's true. Well, that's true, but there are also infinitely many points that are not solutions. For example, all of these points out here. So if you say there are infinitely many solutions, it's true, but that's not specific enough. Where are all the solutions? It's not like every point in the world is a solution, just the ones on these lines. So when we have this situation, we're going to have to take a moment and actually be a little more specific than just say infinitely many solutions. We'll see that when we get to an example of this in a moment. Whenever you have a system of equations, if you have any solutions, whether they be 1 or 2 or 20 or infinitely many, you have what's called a consistent system. That should be an E, shouldn't it? There we go. There we go. That should be an E. So here, this is a consistent system because it has at least one solution. Right? In fact, there's exactly one. This is also a consistent system because it has at least one solution. Infinitely many is at least one. This one has no solutions, so this is called an inconsistent system. Not consistent. Inconsistent system. So that's a definition that we need. Definition. A system of equations is called consistent if it has any solutions, if it has one or more solutions. Now you might say, well, why don't you just say one or infinitely many? Whenever we're dealing with linear systems, those are the only possibilities. The only consistent linear systems either have one solution or infinitely many. There is the possibility that we deal with systems that are not linear, in which case you may have consistent systems that have 2 solutions, or 3, or 4, or 5. We're not going to deal with any of those, but that's the reason the definition is stated the way it is, because when you move away from linear systems, you may have consistent systems with more than one solution, which still are not coinciding lines. Another definition. A system. There should be no S on that, right? A system of equations. There you go. A system of equations has dependent solutions dependent. I keep switching my A's to E's for some reason. There we go. Has dependent solutions. Oh, sorry, has dependent equations, not solutions. If those equations represent the same line. They may not look identical, but when graphed, they are the same line. So here, these are dependent equations. That whatever equations were graphed here are dependent because even though they are different equations, they represent the same set of solutions. So here we have a consistent system with dependent equations. If equations are not dependent, then they're called independent. So here we have an inconsistent system with independent equations. And here we have a consistent system with independent equations. All right. So we have three possibilities. A one-solution linear system with which is a consistent system of independent equations. If we have no solutions, then we have an inconsistent system of independent equations. And if we have infinitely many solutions, then we have a consistent system of dependent equations, where again a system is called consistent if it has one or more solutions, and is called dependent if the equation, and the equations are called dependent if they represent the same line. Now, there are several ways to solve a system of equations. Right now, the first one we're going to look at is the graphical method, meaning if we can graph the linear system of equations, we should be able to find a place where they cross. Or we should be able to find that they don't cross. Or we should be able to find that they are the same line. All right, so let's take a look at some examples of using graphs to solve a system of linear equations. One little disclaimer, you don't always solve a system of equations using a graph. Because if your solution is a nice set of whole numbers, 1, 5, 6, 2, then that's easy enough to pick up out of a graph. But if your solution is something like 3/8, -5/6, that would be very difficult to pick up out of a graph. Whenever your numbers are decimals or fractions, illustration is a difficult way to represent it. It's a difficult way to find that result. So in those cases, we'll have to rely on other techniques. For example, the addition method of solving systems of equations and the substitution method of solving systems of equations. We'll look at those later, but for now, we're looking only at the graphical method. So let's take some examples of using the graphical method to solve a system of equations. Okay. So example, we're going to solve the system. Sometimes it'll say solve the system of equations, but since the only kind of system we deal with is systems of equations, we can just say solve the system, and that'll mean the same thing. So we're going to solve the following system. 6x minus y equals negative 9, and x plus 2y equals 5. Okay, so to solve this system, what we're going to do is we're going to graph these two equations and see what happens. Either they're going to cross somewhere, they're going to be the same line, or they are never going to cross. All right. To solve the system, let's begin by graphing this first equation, and we can either find individual solutions and connect the dots, or we can write this in slope-intercept form, and since that y is almost by itself already, I'll probably have an easy enough time just solving for y. So let's see here. If I have 6x minus y equals to negative 9, I can go ahead and subtract the 6x from both sides. 6x minus 6x goes away, leaves me minus y equals minus 6x minus 9. And then if I divide everything by a negative 1, that doesn't change any of my numbers, but it does change all their signs. So this will give me y equals to positive 6x plus 9, just like that. Okay? So let's go ahead and graph this. Now, when we use a graph to solve a system of equations, we want to be careful with our graph. We want to be as accurate as possible. So although normally here I would only go through and just mark off lines more or less accurately, here I'm going to go ahead and actually use my ruler and do things a little more carefully. So here I'm just going to put a tick mark every 2 sixteenths, every 1/8. All right, so let's see, that's going to be 1, 2, 3, 4, 5, 6, 7, 8. Okay? And then down this way, I'll do the same thing. I'm going to say every 8th. So 1, 2, 3, 4, 5, 6, 7, 8. Whenever you're using a graphical method, I suggest you have some kind of measuring instrument. If you don't have a ruler handy, you can always take a small piece of paper and simply make notations along the edge, something like this, and say, okay, I'm going to go ahead and, all right, there's one, and let me slide that over. Okay, there's the next one. Let me slide that over. Okay, there's the next one, on down the line. If you don't make it at least reasonably accurate, at least reasonably well spaced out, it's going to be very difficult to find your result using the graph. All right. This is another reason why we sometimes use the alternative techniques of the addition and substitution methods. However, the graphical method is a nice way to get started, and it is useful, especially when your equations are simple with nice whole numbers. All right, so let's see here. It looks like I have a y-intercept of 0, 9. And x is equal to 0, y is equal to 9. So it's going to go up 1, 2, 3, 4, 5, 6, 7, 8, 9. Ooh, it looks like haven't gone up far enough. So what I'm going to do is I'm going to count by 2s. And so that's 2, 4, 6, 8, 10, 12, 14, 16, like that. Same thing on this side. I'll say 2, 4, 6, 8, 10. 2, 4, 6, 8, 10, and 2, 4, 6, 8, 10, like that. All right. So if x is equal to 0, y is equal to 9, and so I have a y-intercept of 0, 9. So 2, 4, 6, 8, there's my 9. Okay. Now I have a slope of 6, which is the same as saying 6 over 1. So the top number tells me to go up by 6. And it's either up or down, and positive is up. And the bottom number tells me either left or right, and since that's positive, then I have to go to the right. So from here, I'm going to go up 1, 2, 3, 4, 5, 6, and then right by 1. Just like that. And so here we can go ahead and connect our points to create our graph. And it's It's never going to be quite perfect. It's difficult to draw things freehand like this, but we do the best we can to try to come up with as accurate a graph as possible. All right? We can do the same thing for this other equation. Now remember, we don't have to use the same technique. We can use the slope-intercept form. We can also go ahead and find individual solutions, and that's fine. Let's go ahead and graph this other equation. Let's see, that's x plus 2y equals to 5. Here I could find individual solutions. I could set y equal to 0. Okay, let me do that. If I set y equal to 0, that's going to give me x plus 2 times 0 equals 5. Since 2 times 0 is 0, we can ignore that, and we're simply left with x equals to 5. So that's going to be one solution. When x is equal to 5, we get y is equal to 0. And we could say y is equal to 1, for example. So here we can say, let's set y equals to 1. Yeah, that's fine. And we can say that's x plus 2 times 1 is equal to 5. Okay. From here we can go ahead and subtract this 2 over. Subtracting 2 from both sides would give us x equals 2. 5 minus 2 would give us 3. So here that's another solution, 3 comma 1. So we can go ahead and plot both of those and connect our dots. 5 comma 0 would be here. Let's see, 2, 4, 5 comma 0 right there. And then 3 comma 1 would be 3 to the right, so 2, 3 up by 1. Right about there. And so we can connect our dots. Just like that. Okay. So from the illustration, it seems apparent that we do have one solution. These are definitely not parallel lines, so it's not like we have no solutions, and these are definitely not the same line. So it's not like we have infinitely many solutions. So it's got to be this point right here. Notice this point is a little bit before, and remember I'm counting by 2's here, so this is before 2. So that's probably, what, 1? Oh, but it's to the left, so it's going to be negative 1. And then I've gone up 2, 4, well, no, I haven't gone up to 4, so a little bit more than, so between 2 and 4, that's got to be 3. So to get here, I go 1 to the left, and up by 2, 3. So negative 1 comma 3. Okay. If you don't have a pen that's quite as sharp as mine, I have a very fine point pen here, you might want to make your graph a little bit bigger. Do whatever you need to make it as clean and clear for yourself as possible. Okay. Negative 1 comma 3, now we believe that's the solution. A limitation of using a graph is that you can't really be completely certain. Maybe our drawing is slightly crooked, or maybe I'm seeing something just a little higher or a little bit lower than I thought I should. So here we need to test this. We need to make sure, because maybe it's not negative 1 comma 3. Maybe it was negative 1 comma 4, and I just drew I just have my drawing a little crooked. So here, let's go ahead and check these to confirm. Okay, we're substituting in, so it's going to be 6 times negative 1 minus our y value is 3, and we think that should equal to 9. Let's see what happens. Negative 1 times 6 is negative 6, and negative 6 minus 3 is in fact negative 9. So yes, that one works. Now remember, a solution must be a solution to a system must solve both equations. So we know it solves the first one, but we still got to check the second one. Even if it works for the first one, it might not work for the second. So let's go ahead and check the solution negative 1 comma 3 in the second equation. So that's going to be negative 1 plus 2 times 3, and we think that's equal to 5. 2 times 3 is 6, and if you add negative 1 with 6, you're going to get 5. So yes, that one works as well. So because that point works as a solution to both of our equations, that means it is the correct solution to our system. Solution to the system. And there we go. So go ahead and give this a try. Oh, actually, I suppose before you try one, let me go ahead and let's look at some more examples here. Because after all, we've only covered one possibility. Let's talk about some other possibilities before we have you try it. So let's go ahead and solve our system. X minus y equals to 4, and negative 3x plus 3y equals to 6. Okay? All right, so we're going to do the same thing. We're going to graph both of these equations, and we're going to see what happens to the graphs of these equations in the system. Let's see how they interact. We can go ahead and, again, write in slope-intercept form and graph that way, or we can find individual solutions and graph that way, and it makes no difference, so just pick your favorite. Here, I'm going to go ahead and put things in slope-intercept form and see what happens. This first equation, well, let's see, I can subtract the x over this way. So let me go and do this off to the side. X minus y equals to 4. I can subtract the x from both sides of my equation. It'll give me minus y equals to minus x plus 4. And then if I divide everything by a negative 1, negative over a negative is a positive y, negative over a negative is a positive x, and positive divided by a negative is a negative 4. All right, so there we go. That first equation is y equals x minus 4. So let me go ahead and graph that. Okay, let's see here. So I'm going to go up. Let's see here. 1, 2, 3, 4, 5, 6. And then I'm going to go down. 1, 2, 3, 4, 5, 6. And then I'm going to go left and right. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Notice I am taking the time to graph this very carefully, and in a video where I can edit things out and where I can speed up things, I'm choosing not to, because again, this is an important part of the process. Whenever you're using a graph to solve any system, you need to be as accurate as possible. Otherwise, it's not going to be possible to use the graph to solve the system. All right? So here we go. We're going to go ahead and graph y equals x minus 4. Okay, well, when x is equal to 0, then that means y is equal to negative 4. So 0, negative 4 must be our y-intercept. Right there, 0, negative 4. And then I have a slope of 1, which is the same as saying 1 over 1. So from here I can go up 1 and right 1. Okay. So let me go ahead and do that. I go up 1, right 1. All right, 1 over 1, up 1, right 1. And now I can go ahead and connect my dots. Like that. Okay. So that's the first equation. Now let's go ahead and graph the second one. I can do the same thing. I can go ahead and find individual solutions and plot them, or I can put things in slope-intercept form. For this one, let me go ahead and find individual solutions. It doesn't really matter, but here I'm trying to illustrate both methods. So I'm going to go ahead and graph negative 3x plus 3y equals to 6. Let me go ahead and set x equal to 0. Okay, well, if that happens, that's going to be negative 3 times 0 plus 3y is equal to 6. Of course, here, 0 times anything is 0, so that just leaves me 3y is equal to 6. And if I divide both sides by 3, I get y is equal to 2. Okay, so that's going to be one solution to that equation. X is 0 and y is 2. And if I do that for the other side, if I set y equal to 0, well, that's going to give me negative 3x plus 3 times 0 equals to 6. Of course, anything times 0 is 0, so we can get rid of this. And if we divide both sides by a negative 3, 6 divided by a negative 3, that's a negative 2. So we have a solution of negative 2 comma 0. Okay. So let's go ahead and graph that. Negative 2 comma 0, that's 2 to the left, and we don't go up or down at all. So that's right there. And then we have 0, 2, which means that's a y-intercept of, again, 0, don't go left or right. 2 means up by 2. And now we can connect those dots, and we create a graph. And notice that these lines are not connecting. They're not intersecting each other. Now, you might be wondering, well, maybe I just drew it wrong. Or you know what, maybe if I keep going, here we didn't go very far, we only went up as far as 5. Maybe if we kept going, eventually they would cross. Well, the other thing to note here is they both have a slope of 1. Because from here to go, we went up 1, right 1. Over here, to get from this point to this point, we would go up 2 and right 2. Oh, but what's 2 over 2? That's the number 1, isn't it? So here, this has a slope of 2 over 2. Which is just the number 1. And over here, from looking at the slope-intercept form, we also saw that this one had slope is equal to 1. So if they have the same slope, that means they're going to travel in the same direction. So that means they can't get any closer together or further apart. So even if you look at this and think, well, maybe I just didn't draw it far enough. Maybe if I kept going, I would eventually see them cross. No, because they have the same slope, that means that they're traveling in the exact same direction, which means these can never cross. So this is an example of an inconsistent system. In other words, we have no solutions. There are no solutions. This is an inconsistent, oops, that should be all one word, inconsistent system. And there we go. So if ever you have two parallel lines, meaning two lines that have the exact same slope, that means your graphs will never cross. And this inconsistent system means there are no solutions. Right? Let's take a look at another example. And the same kind of question. We're going to go ahead and solve the system. Consider the system x plus 3y equals 0 and negative 2x minus 6y equals 0. Okay, we're going to go ahead and solve the system through graphing, and once again, I'm going to go ahead and do one using the slope-intercept form. I'll do another one using individual points, and either way, we're going to get our graphs. All right, so let's take a look. I'll do, just like the last two examples, I'm going to go ahead and do the first one with slope-intercept form. When you do problems, if you want to do both of them with a slope-intercept form, that's perfectly fine. That'll work. If you want to do both of them by finding individual solutions and connecting the dots, that's fine. Or if you want to do one of each, that's up to you. As long as you find the graph one of those ways, then you'll get your result. So here, this first one, I'm going to go ahead and put everything into slope-intercept form. Let's see, if I have x plus 3y equals to 0, I'm going to subtract my x over to the other side. That'll give me 3y equals to negative x. I could say negative x plus 0, but there's no point in writing a plus 0 here. If you want to, you can. Then I can divide both sides by 3. Now remember, negative x is like saying negative 1 over x. So these 3's divide away to give me y. And here, negative 1 over 3, well, that's negative 1/3. And then don't forget your x. All right, so there we go. This top equation can be graphed as y equals negative 1/3 x. Notice that means that if x is equal to 0, then y is equal to 0. Anything times 0 is 0. So that means that here, this is going to cross through the origin. When x is 0, y is 0. Okay, so let's go ahead and see what that looks like. And for some reason I've decided to go with centimeters, and that's fine. It doesn't matter what our measurement is as long as it's uniform. All right, so let's take a look. We know this is going to cross through the origin because here there is no constant, which means whenever x is equal to 0, anything times 0 must be 0. So when x is 0, so is y. Okay, so that's going to cross through the origin. And then note that this has a slope of negative 1/3. Okay, so negative 1 means we're going to go from here, we're going to go down 1. And then the 3, that's positive, so we're going to go to the right by 3. All right, negative 1, that means you're going to go down by 1. Positive 3, that means you go right by 3. So down 1, right, 1, 2, 3, right there. And so we can go ahead and connect our points to form our line. Okay, let's go and try the other one. The other one I can go ahead and do using individual points. Again, if I want to use slope-intercept form, I can, but here I'm trying to represent both of them so that you have plenty of examples of each. Okay, so let's go and give that a try. We're going to take negative 2x minus 6y equals to 0. And here I'm simply going to plot a couple of points here. So let me plug in y is equal to 0. Let's see what happens. If I set y equal to 0, that's going to be negative 2x minus 6 times 0 equals 0. Okay, well 6 times 0 is 0, so we can just ignore that. That gives us minus 2x is equal to 0. And to get that x by itself, I can divide both sides by 2. Oh, sorry, there should be a negative 2. And so that gives me an x is by itself now. Here, 0 divided by some number, that's still going to stay 0. Okay, so there we go. When x is equal to 0, y is equal to 0. That's going to be one solution to this second equation. Okay, so then 0, 0. That's a point they have in common. Let me go ahead and find one more solution. Let me just use y is equal to 1. Let me set y equals to 1. Okay, well in that case, I have negative 2x minus 6 times 1 is equal to 0. Okay, so that's just the number negative 6. Negative 6 times 1 is negative 6. So I can go ahead and add 6 to both sides. Makes this go away. 6 minus 6 is 0. And that leaves me just a negative 2x, which is equal to 6. And then I can go ahead and divide both sides by negative 2. And that leaves me an x, which is equal to 6 divided by 2 is the number 3. Okay, so I have a solution of 3, comma... Oh, I'm sorry. That should be a negative 2, shouldn't it? I divided by a negative right here. There we go. So that's 6 divided by negative 2 is negative 3. Okay, so I have a solution of negative 3, comma 1. All right, so negative 3, I'm going to go left by 3 from the origin, and then up by 1. Okay, so from here I'm going to go left by 3, 1, 2, 3, and up by 1. So I'm going to have the line that connects, here let me do these in two different colors. Here's the line that connects 0, 0 with negative 3, comma 1. But notice what happens when I connect those dots. It's the exact same line that I had before. So here, even though I had two equations, they look different. They have different constants. They have different coefficients. They have different signs. When graphed, those two different equations represented the same line. So this has a pair of dependent equations, which means that we have infinitely many solutions. This system has two dependent equations. So it has we have infinitely many solutions. But I mentioned earlier that that's not sufficient. And that's not enough to be a full answer. Because yes, it's true. This does have infinitely many solutions because this point is a solution to both equations. And so is that one, and so is that one, and that one, and that one, and that one, and so on. Forever. But I can't just say every point's a solution because look, this point over here is not a solution to those equations because it's not on the graph. Same thing with this point, and this one, and this one, and this one, and this one, and this one. There are infinitely many points that are solutions, but there are also infinitely many points that are not solutions. So just say there are infinitely many solutions is not sufficient. It's not enough of an answer. Okay, so how do we state our answer? Well, what we want to say is that our answer is all of the points that are on either of these lines. Well, yeah, but it's not really two different lines. It's really just one line. Okay, so what we want to say is our solutions to our system are all the points on this line. There's only one. Okay, well, how do you describe this line? We already did. This equation, y equals mx plus b, in this case b was 0, this is a description of this line. Now, technically all of these are descriptions of the line, but this is the most commonly used one, the slope-intercept form. So, whenever we're going to express the solutions of a system of dependent equations, what we want to do is we want to express that it's not just infinitely many points, but these infinitely many points, the ones that are on this line. So here's how we write it. We can't actually list a full set. If it was one solution, we would say, okay, here's the solution. If there was 2 of them, 3 of them, 4 of them, we would just list them. But there's no way to list infinitely many points. So instead what we do is we describe them. Here's how we describe them. We say, this is what our solutions are going to look like. They're going to look like x comma y. Okay, sure, they're going to look like points. Can you be more specific? Sure. They're going to be points, x comma y, such that this little vertical line, this separates what your point's going to look like to the conditions on that point. It's read as such that. Whenever you see a vertical line like that, this is read as such that. It's points x comma y such that y is equal to negative 1/3 x. What this does is it gives you a description. It says anytime you have a point where if you take your x value, multiply it by negative 1/3 and you get your y value, that point is one of the solutions to this system. Now notice this isn't just a single point. It's infinitely many. It's a full set of solutions. Whenever we have a set of solutions, we write it in the set notation. Whenever you have set notation, you use these curling braces. This tells you this is a set of things. It's not just a single point that looks like that. It's a whole set of them. And there we go. This is the accepted way of writing a solution set to a dependent system of equations. All right. So go ahead and give this a try. So now I'm going to go ahead and give you an example. To try, and it's either going to be a inconsistent system with no solutions. It's going to be a system of dependent equations with infinitely many solutions. So you have to write it like this, or it's going to be a independent system that is consistent, meaning you have just a single solution. Those are the only 3 possibilities. So go ahead and give this a try. You're going to solve the system. X plus y equals to 4, and y equals x minus 2. Notice in this case, this was already given to you in slope-intercept form. That'll happen sometimes. In this case, you're probably better off just graphing it this way. Yeah, you can find individual solutions, but since that's already in slope-intercept form, you probably just want to go ahead and use that. But it's not a requirement to use any particular method. As long as you can graph them both, go ahead and give that a try. Pause the video, and once you are done and have found a solution to the system, or have found that there are no solutions, go ahead and unpause the video, and we'll go through it together. All right, so let's take a look. Let me go ahead and graph both of these using the slope-intercept form. All right. Here, this one's already in slope-intercept form, y equals mx plus b. Here, your slope is just the number 1. Here, this one's almost in slope-intercept form, so you have to subtract the x from both sides. So here, let me go ahead and rewrite this one. If I just subtract x from both sides, that isolates my y. And now over here, I have a minus x plus that positive 4. So let me graph both of those equations. All right, so here we go. In this first equation, I have a y-intercept of 0, 4. When x is equal to 0, that goes away, and I'm left with y is equal to 4. So 0, 4 is my y-intercept. Okay. I'm graphing this one right now. Since my slope is negative 1, or notice that's negative x, which is the same as saying negative 1 over 1. That means that I have that's negative 1 on top over 1 on the bottom. So from this point, I'm going to go down 1 step and right 1 step to right about there. And of course, now I connect my dots, and that gives me my result. Now, this other equation was already in slope-intercept form. So let's go and give that a try. Let's graph this one. That's got a y-intercept of 0, negative 2. If you go ahead and set x equal to 0, that means your y, that x goes away, and so y is equal to negative 2. So it's going to be down here, 0, negative 2. And now my slope is positive 1, which means I go up 1 and right by 1. Like that. And so now I can connect those points and get myself a result. Okay. So there we go. I've gone ahead and graphed both points. It looks like I do have a place where they cross, and that's that point right there. So this is definitely not an inconsistent system. We do have some solutions. And these equations are not dependent. They don't graph the same line. So in this case, you have one solution. And let's see what that solution is. It looks like to get to this point, I would go right 1, 2, 3 steps, and then up by 1. So it looks like this is the point 3, 1 is the solution. All right, but of course we should check this because after all, this is a graph which, if you're off by a little bit, might give you an incorrect answer. This might not be 3, 1. It might be 3, 1.5. I might have graphed things a little crooked. So let's just go ahead and give this a try. Let's check this. If x is equal to 3 and y is equal to 1, 3 plus 1 is equal to 4. Okay, that works as a solution to my first equation. What about my second equation? If x is equal to 3 and y is equal to 1, 3 minus 2 is equal to 1. Yeah, that works. So we substitute these x and y values into our equations, and if both of them are true, that means that yes, we did things correctly, and this is in fact our solution. And there we go. Okay, we're going to go ahead and try one more. Go ahead and give this a try. Solve the system. (3x minus 4y equals to 12), like that. And just to make it look like the other one, y equals 3/4 x, let's see here, minus 3. Like that. So in this case, one's already in slope-intercept form, the other one is in standard form, and that really doesn't affect what you need to do. You're still going to go ahead and graph and use the graph to solve the system. So go ahead and pause the video and give this one a try as well. Once you are done, go ahead and unpause and we'll go through it together. All right, so this bottom equation is already in slope-intercept form. So let me just take advantage of that and graph it in slope-intercept form. Okay. Okay. We have a y-intercept of 0, -3, because if x is equal to 0, that goes away. We have y equals -3. Okay. So that is our first point. Now we have a slope of 3/4. Top number tells you up and down. In this case, since it's positive, we're going to go up. The bottom number tells you left and right. Since that's positive, you're going to go to the right. So from here, we're going to go up 1, 2, 3, and right 1, 2, 3, 4. Up 3/4. And we can go ahead and connect our dots and get our result. Connecting these 2 points gets us the graph of this first equation. Okay. Now let's take a look at our second equation. This one is in standard form, so we can put it in slope-intercept form if we like, or we can go ahead and graph individual points. Either one's fine. Here, let me go ahead and graph individual points. The equation 3x minus 4y equals 12. If I set x equal to 0, well, that's going to be 3 times 0 minus 4y equals to 12. Anything times 0 is 0, so that goes away, leaving us just minus 4y equals to 12. Then we can go ahead and divide both sides by a -4. These two divide out, giving us y equals 12 divided by -4. Positive divided by a negative is a -3. All right, so there's our x value, our y value is 0. There's our x value, our y value is -3. So we have a point 0, -3. Okay, so 0, -3 right here. Okay. I can go ahead and do the same thing for y equals to 0. Let me go ahead and set y equals to 0. That's going to give me 3x minus 4 times 0. My y is now 0, equals to 12. Anything times 0 is 0, so that goes away, leaving me just 3x equals to 12. And then I can divide both sides by 3 to isolate my x value. So here this x is now by itself, and I have 12 divided by 3, which equals to 4 as my x coordinate. So that gives me a solution of x equals 4, y equals to 0, 4, 0, like that. And if we plot that, that's 4 to the right, and then we don't go up or down at all. That's that point right there. And if you note, that's exactly the same 2 points that we had before. But even if they weren't the exact same 2 points, all that matters is that whatever points they are, they plot the same line. So again, even if I had this point and this point for one equation, and this point for another equation, it doesn't matter what specific points I have. What matters is that those points connect to give me the exact same graph. So because of this, I have a system of dependent equations. with two solutions. With infinitely many solutions. From just those two. Right? But of course, if we have a dependent set of equations, then we can't just say you have infinitely many solutions. It's true, but that's not specific enough. So the way we write that is we take the representation of this line in slope-intercept form. Now, either of these represent the same line, so it doesn't matter which one of these we use, right? That one or that one. But since that second one is already in slope-intercept form, I might as well just use that one and have less work to do. So my result is I have a set of solutions, x comma y. Okay, well, what about them? Are there just any x comma y? Well, no, they're the points x comma y such that y equals 3/4 x minus 3. 3/4 x minus 3. So wait, is it just one point like that? No, it's a whole set of them. In fact, it's all of them. Okay, so then we're going to go ahead and write it as a set to signify the fact that we don't just have one solution like that. It's a set of solutions. It's every solution that could fit inside that set. So this right here would be our final result. This is our solution, or solutions to our system of equations. And that's it. That's it for this video. If anybody has any questions, comments, or problems, please make a note of those, reach out, and I'll get back to you as I can. I hope everyone has a nice day.